Untitled here at Katana, entitled Parallel Rheology and Grade Correlation Length at the Jamming Transition.
Thank you very much. I will be talking about rheology, in particular rheology in dense granular material. And what I'm going to talk about involves the concept of jamming transition, which describes the kind of phase transition between the solid phase and liquid state of granular material. And my interest lies in rheology, so that this solid and liquid distinction corresponds to solidification or fluidization of granular material. And my talk involves only numerical results, so that no theory so far. And also, I use a very simple model, which is frictionless spheres, so that it might be too simple to be useful in the field of industrial society or something like that. But for these simple models, we can observe highly non-trivial behaviors, such as which is the power of rheology. And this is non-trivial dependence of the shear stress on the shear rate with exponent x gamma. And this exponent is not 1, which corresponds to Newtonian viscosity, nor 2, which corresponds to the Bagnode scaling, but it's a non-integer exponent. So this is the power of rheology, which I'm going to talk about. So let me briefly introduce the concept of jamming transition. So in one line, the jamming transition is acquisition of the rigidity of granular material. So the important parameter here is the density. And if we start from the lower density regime and then increasing the density, and at some point, we observe non-zero rigidity, also, which is a non-zero shear modulus. But below this threshold density, granular material behaves like fluid, so that there is no rigidity or no shear modulus. So this is fluid-like and solid-like, so that jamming transition can be regarded as the phase transition of granular material, which corresponds to a kind of first-order-like phase transition. So the important point here is that this threshold density, called the jamming density, is unique if we involve frictionless particles. So that's why I'm working on this simple model. And this jamming density is approximately 64% in the volume density in 3 dimensions and 84% in 2-dimensional systems. And of course, if we utilize the frictional particles as usual, we can observe such phenomena. But in this case, jamming density is not unique. In other words, it depends on the history with which we prepare the system. So in another view, the jamming transition can be regarded as the emergence of force chains between particles. So below this jamming density, we have no force chains, but above this density, force chain develops. So in terms of rheology, the jamming transition can be viewed as the emergence of yield stress. So that if we take shear stress as another parameter, and below the jamming density, we need infinitesimal shear stress to let the system flow. But at higher density, we need non-zero shear stress to let the system flow. So in more general context, we add the temperature as state parameters. So if the particle size gets smaller and smaller so that the conventional temperature comes into play, we can discuss also glass transitions, unifying the concept of granular rheology and also glass transitions. But we only consider here zero temperature plane, which represents the granular media. So our interest is how this jamming transition point, which we call point J here, how this point J affects the rheology of granular matter. And it is suggested that point J is a critical point with some numerical evidences. So jamming transition can be viewed as a second order phase transition, and some interesting properties are due to the fact that the point J is a critical point. So we introduce here a computational model which we adopt. This is a frictionless system, so that we have only force along the normal direction to the relative vector of two particles. So this force consists of two terms, and the former is elastic force, which acts also only repulsive force. And the second term is responsible for the dissipation. Using this simple model, we discuss the rheology. And this is a computational system we adopt. And we use so-called throttle equation by which the shear is continuously put on each particle level. So it ensures uniform shear flow. And we utilize the Lee-Edwards boundary conditions. This is more like periodic boundary conditions, but the adjacent cells are continuously displaced in accordance with the shear strain. Also, we use bidispersed system to avoid crystallization. And we check, we investigate both two-dimensional and three-dimensional systems so that we can discuss the dimensional dependence of rheology. So let us going into some results of this numerical system. And this is the rheology of granular system at various density, but it's near the jamming density. So that this is the shear rate and shear stress. So if we start from the lower density, we can observe the Bagnode scaling in which the shear stress is proportional to the square of shear rate. And also at the higher density, we can observe yield stress. And the threshold density, which divides the Bagnode scaling and this yield stress-like behavior, is of course the jamming density. And at the jamming density, it is suggested that the shear stress obeys a non-trivial relation like this. So also we find this scaling law which describes the granular rheology in a unified way. And this is raw data of the rheology. And by using this scaling law, these data fall onto a master curve. So that with these exponents. So this is of the same form as the scaling laws in conventional critical phenomena. So it is another evidence for the point J being a critical point. So this is a three-dimensional result, but in two-dimensional cases, the result is essentially the same, and the exponent and the scaling functions are the same for two-dimensional systems. So this scaling law implies some important points, which are described here. And the important point is that this scaling law implies the dynamic yield stress, the behavior of the dynamic yield stress like this, and also the power law rheology at the jamming density. Critical exponents obtained here suggest that this exponent should be 0.63. So we directly compute the rheology at the jamming density. So if we prepare the large enough system to avoid finite size effect and then tune the density at the jamming density so that we can observe power law rheology up to 4 decades. But we don't understand why this such strange rheology appears at the jamming densities, and the physical mechanism is still open. And also the interesting property regarding the power law rheology is that we can find the strong finite size effect. And this is a rheology of different systems of different size. And this figure shows that we obtain a higher shear stress for smaller systems. So that if we prepare this small system, which consists of about 50 particles, the shear rheology obeys the power law rheology, but suddenly deviates from the power law rheology and going like this. And also, if we prepare the larger system, it goes like this, but suddenly it deviates from the power law rheology. So this is the finite size effect. And this property can be interpreted as there exist some growing correlation lengths, which increases as the shear rate decreases. So that if the correlation lengths exceed the system size, the cooperative motion of particles is suppressed so that such hardening occurs. So we can do a finite size scaling as in the conventional critical phenomena. And assuming this form of scaling law, these finite size effect collapse onto a single curve. And this scaling law implies that there exists the correlation length which diverges as the power of the shear rate with this exponent. So we will detect this correlation length at the particle level in the next section. So what we utilize here is that this kind of spatial correlation function, which characterizes the spatial heterogeneity of particle velocity. So the order parameter for each particle is denoted by m sub I, and this is 1 for slower particles and takes 0 for fast particles. And then this is a scaling form of this spatial correlation functions, which suggests that this the correlation length defined by this correlation function diverges like this with this exponent, so that this correlation length defined by this correlation function is consistent with the finite size scaling. This is a direct visualization of the spatial heterogeneity of the particle's velocity. And this is for a higher shear rate, and this is for lower shear rate. But for these systems, the density is the same, so that we can see that the correlation length of particle velocity increases as the shear rate decreases. And here, the blue particles represents the particles of larger velocity, and the red ones represents particles with smaller velocities. And also we have a movie. A motion of such heterogeneity is like this. It's slowly moving. So that, but we don't know how these velocities correlates. We have checked that such kind of chain-like collisions, which is quantified by such correlation function, but the correlation length defined by this correlation function shows a very slow increase, so that this kind of motion is not the answer for the growing correlation length at the jamming density. So the last section is the time scale, which corresponds to these correlated motions. And this is the mean square deviation of each particles as a function of time. So that the motion of the particles are ballistic at the shorter time scale, and then going to diffusion. And then there exists a time scale above which the particle motion becomes diffusive. So that this time scale defines structural relaxation of our system. And this correlation length increases as the shear rate decreases. Correlation time increases like this. And this scales to the correlation length with some exponent z, which is approximately 3 in 3-dimensional system. So we obtained essentially the same results for 2-dimensional systems. Also power of rheology and finite size effect, and correlation length of the dynamical heterogeneity. That this the structure relaxation time depends on the dimensionality, which at which we obtain z equals 2 for 2-dimensional system. So this quantity is dimensionally dependent. So it seems that I have two more minutes. Okay. So then we go into the last section, which discuss the fluctuations of shear stress. This is the temporal fluctuation of shear stress. And if we are at higher shear rates, the fluctuation is very small. It fluctuates around the mean value. It should be mean value, but it is lower. But you can see the fluctuation is very small for the higher shear rate system. But the fluctuation is very large if we obtain the finite size, if we encounter the finite size effect. And interesting property with regard to this finite size effect and large fluctuation is that we can obtain the Gutenberg-Richter's law, which is known in the seismology. So that what we did is we record the time evolution, temporal fluctuation of elastic energy, and with this temporal profile, we can define the sudden energy drop, which corresponds to a kind of earthquakes. So that this represents the magnitude of earthquakes, micro earthquakes in granular material. And the distribution of each event obeys this form, which represents Gutenberg-Richter's law. And this exponent is important in seismology, which represents this green line. And this exponent also depends on the dimensionality of the system. And this value is 1.4 in two-dimensional systems and 0.7 for three-dimensional systems. And earthquakes in real life obeys Gutenberg-Richter's law with this exponent, so that for three-dimensional system, we get very similar phenomena in shared granular material, like an earthquake. But it is important to call your attention to the fact that we can observe earthquake-like phenomenon only this region in which the finite size effect comes into play. So this is a summary. We obtained power rheology with non-trivial exponent and growing correlation length by using the velocity correlation functions. And also this is the behavior of the structural relaxation time. Yes, but there are so many open questions that we have no theories so far, only numerical simulations, so that we wish to interrelate these two behaviors, like the dynamic critical phenomena. And also, this may relate to the, we wish to know the origin of Gutenberg-Richter law. Maybe this simple granular system may be of help to understand this, this Gutenberg-Richter law. And thank you for your patience.
A couple of questions. Okay.
Have you varied your particle stiffness?
Particle stiffness, no.
Okay, you'll find a lot of things will fall into place if you do, because it governs change. If you increase the particle stiffness or decreases it, it changes your structural relaxation time. It'll also affect the, since it affects the rate at which particles break apart, after they come together, it will explain your shear rate dependence on your correlation length. You'll find that that will vary as your particle stiffness changes. Because what it means is that you're pushing it together faster relative to the time it takes the particles to break apart.
Yes, and we haven't changed the stiffness, but we have changed the force law. Here we adapt linear force, but we have also tested the Hertzian contact law. But the result is
it all works more or less the same. It's just, I mean, it'll be slight. It'll have different power law dependencies. But
yes.
But by changing the stiffness, you're going to change your time scales, and that will resolve a lot of the a lot of the missing bits in here, because as to what scales your what they call structural relaxation time. Well, you can scale that out of the problem. You'll probably be able to scale out your shear rate also.
Thank you for your comments. Yeah.
As you're probably aware, there's been a proposal for a different approach to the point J, that it maps onto the statistical model of K-core percolation. Is there any way of using that kind of percolation approach to understand the scaling in the direction that you are approaching point J by reducing the shear rate?
Reducing shear rate. Yes. Yes, it's right. To my understanding, K-core percolation, the K-core percolation is investigated by using the mean field approach, right? So, what I do not understand is how we can put K-core percolation in this safe space, but there is no rheology,
Right.
but no temperature. Maybe there is some quantity which corresponds to density, but I have no idea on this subject. Some people do working on such K-core percolation like a random graph model, but I don't understand the relation between these abstract models and particulate models. So, sorry.
Okay, well, just one last question then, please.
You share the system, does the normal stress also change?
Right. Normal stress also changes.
Is the scaling law the same as that for the shear stress?
Almost the same within the range of the numerical estimation